In this video, we'll cover thermal equilibrium. So what is thermal equilibrium? Well, if we take two objects and place them in thermal contact, eventually they'll come to the same temperature. When they do, we say that they are in thermal equilibrium. The 0th law of thermodynamics says that if two objects are each in thermal equilibrium with a third object, then they are also in thermal equilibrium with each other. So here's an example. If the object here, T1, is in thermal equilibrium with T3, and T3 is in thermal equilibrium with T2, then T1 and T2 are also in thermal equilibrium. Three objects, A, B, and C, initially have different temperatures. A has the greatest temperature, then B, and C is the coolest. Objects A and B are separated by an insulating plate, which is purple on the screen. They are in contact, though, with object C by a conducting plate, which is light blue. Which of the following is true when objects A and B reach thermal equilibrium with object C? A, the temperatures of all three objects do not change. B, object A has a higher temperature than objects B and C. C, object C has a higher temperature than objects A and B. D, objects B have a higher temperature than A and C. And E, all three objects have the same temperature. Okay, let's check the answer. The correct answer is E, all three objects will have the same temperature. Even though there's a thermal barrier, an insulator between A and B, A is in thermal equilibrium with C, B is in thermal equilibrium with C, and therefore A and B must also be in thermal equilibrium with each other. When two objects, which are isolated from their surroundings, are brought in contact with one another, we know that heat will flow from the hotter object to the cooler object until both of the objects reach thermal equilibrium. So here we have before contact. When they contact each other, the hot object will transfer energy to the cold object, and eventually they will reach the same temperature and be in thermal equilibrium. Because there is nowhere else for the heat to go, and because heat is energy and energy is conserved, heat lost from the hotter object plus heat gained by the cooler object must be equal to 0. In other words, the total sum of the heat must equal 0. So let's look at example 1. We have two equal massed objects of water at different temperatures, and they are mixed together. What is the thermal equilibrium temperature, TF? So before contact, the water here is 90 degrees Celsius, and this one here is 10 degrees. We mix them up. What is the final temperature? Well, we know that the change in the heat, the sum of the heats transferred must equal 0. We know that Q is equal to MC delta T, and delta T is T final minus T initial, or T naught. We know that the heat lost from the 90 degrees Celsius water plus the heat gained by the 10 degree water must equal 0. We know that the mass and the specific heat capacity of water is the same for both objects. And so if we substitute in the numbers, we end up with a final temperature of 50 degrees Celsius. A styrofoam cup containing 400 grams of 60 degrees Celsius water is poured into another styrofoam cup containing 800 grams of 15 degree Celsius water. What is the temperature of the combination? Go ahead and pause the video now to solve this problem. Okay, so let's take a look at the solution. We know that the heat lost by the one object plus the heat gained by the other must equal 0. Since both the materials are the same, we can eliminate C. So we have M1 times the final temperature minus the initial temperature of the first object, plus the mass of the second object times its final temperature minus its initial temperature. and that must equal 0. Substituting in the equations, substituting in the temperatures, and solving for the final temperature, we end up with 30 degrees Celsius. So the answer is D. 2 vials of mercury sit on the chemist's desk. One vial contains 80 grams of mercury at 20 degrees Celsius, while the other vial contains 20 grams of mercury at 60 degrees Celsius. She then pours one vial into the other. What is the final temperature of the mercury? Go ahead and pause the video now and solve for the answer. Okay, so let's take a look at the solution. The correct answer is D, 28 degrees Celsius. The heat gained by one material plus the heat lost by the other has to equal 0. Substituting in your numbers, you should end up with a final temperature of 28 degrees Celsius. So let's talk about calorimetry. Often a calorimeter, which is a heat measuring device, is used to find the initial temperature, the specific heat, or other thermal properties of a substance. A simple calorimeter is composed of a container that is insulated from the outside environment, so no heat or very little heat can enter or leave the system. So for our simple experiments, the calorimeter's inner cup may be made of aluminum. The calorimeter will be filled with a quantity of water. We will drop our sample substance from the top before inserting the stopper. So this is a stirrer right here. Usually we have an outer cup and an inner cup. Usually the outer cup can be steel, the inner cup can be aluminum. There's an air barrier between the two cups. Notice here in this case they're using styrofoam as the outer cup and aluminum as the inner cup. And then you have a stopper, which is the insulator, and then you have the thermometer that goes through as well as the stirrer. So this is a very simple calorimeter. Usually the stopper is not a cork. Usually it's a metal lid which has 2 holes in the top, and then it has a black insert which is an insulator so that energy cannot be transferred through that material. Okay, so let's do an example. We have a 0.4 kilogram aluminum calorimeter. It's filled with 0.8 kilograms of water. The calorimeter and water come to thermal equilibrium at a temperature of 20 degrees Celsius. 0.1 kilograms of a material, unknown, U, with a specific heat of 628 joules per kilogram Celsius degree, and an initial temperature of 300 degrees Celsius is dropped into the calorimeter. We want to find the equilibrium temperature of the combination. So now what we're going to do is we're going to add up the energy transfer for all 3 objects. So we have an energy transfer of the water, the aluminum internal cup, and also the unknown object. Okay, so when we add up all of those heat transfers, we should get 0. So we're going to substitute in MC delta T for each object. The change in temperature is T final minus T initial. We're going to substitute that in here. And then we're going to solve for the final temperature. And we end up getting a final temperature of 24.69 degrees Celsius. I can't get rid of that. Okay. There we go. Okay, so now we're going to go ahead and do another problem. We have a 0.1 kilogram aluminum calorimeter. It's filled with 0.5 kilograms of water, both at 0 degrees Celsius. We take a 0.1 kilogram sample of an unknown substance, which is at 210 degrees Celsius. It's dropped into the filled calorimeter. When the combination reaches thermal equilibrium, the temperature is 15 degrees. In this case, now we want to solve for the specific heat capacity of the unknown substance. Go ahead and pause the video now. Okay, so let's take a look at the solution. The heat transferred from the calorimeter cup plus the water plus the unknown object has to equal 0. The heat transferred is equal to mc delta T, where C3 is the unknown specific heat capacity. Substituting in all of the known numbers, we end up getting C3 is equal to 1,674.4 joules per kilogram Kelvin. In this case, they're using Kelvin, but it really is also Celsius degree. Because remember that the change in temperature is the same for both Celsius and for Kelvin. In the next video, we'll talk about phase transitions.